Hi, physics friends. This is Mrs. Taylor here, and we're going to talk a little bit about waves today. I'm trying a different format, so you can tell me whether you like this format or not, or if you prefer the screencast where I'm just talking and you see my things moving on the screen. So give me some feedback and let me know. So I'm going to go ahead and hop out to my presentation because I want to show you what exactly we're going to be doing today with waves. All right, so hopefully at this time you can see my wave characteristics slide. So kind of what is a wave? You've done some exploration with waves on a couple of different applets that we'll look at today. But basically a wave is any vibration in a medium. So when I say a medium, I'm talking about air or water or even a vacuum, meaning no particles at all. Through time. And the purpose or the function of a wave is it carries energy from one place to another. So right now I'm communicating to you through waves. So you're hearing sound waves and you're also seeing light waves. And those two things are communicated or used to communicate to you what information I'm providing. And that is actually a form of energy. So some of the examples that I just listed were light, sound, water waves, the wave in a stadium, right? There's so many different waves. In fact, every time you pick up this, you are using all sorts of waves, right? Cell phones operate on electromagnetic waves. So let's take a minute and label a couple of the basic parts to our waves. So one of the first basic things that we'll need to know is different parts. So we have a crest here and a trough down here. And then the length of a wave would be, sorry, not the length of a wave, but the amplitude would be from this middle line. And this middle line is called the equilibrium position up to that highest point, which is known as the amplitude. And then the length of a wave is known as the wavelength. And you can actually measure the wavelength in a couple of different spots. You can measure it crest to crest. You could measure it trough to trough. You can measure center of the wave, center of the wave. It doesn't matter. Those are all going to be the same length. And we actually use a fun little symbol for wavelength, and it is an upside down Y. It is a Greek letter called lambda. And we'll talk a little bit more about lambda in just a little bit. So there's a couple of different kinds of waves that we'll see. So if you've ever played with a Slinky, you know, and if you have one at home, I highly suggest playing with them because they're fun. You can move the Slinky side to side this way. And the wave actually travels down the Slinky this way. So this is called our wave velocity. And this movement here, that up and down movement of our hand, is called the displacement. We've had that word before, right? And notice how the wave velocity is perpendicular to the displacement. That's called a transverse wave. These are the most common types of waves. Water waves, light waves are all examples of transverse waves. There's another kind of waves that are actually really useful, and that's going to be a sound wave. And this is how a sound wave is produced. This is also called a longitudinal wave. Longitudinal. And you move your hand back and forth on this Slinky, and the wave travels along the Slinky down that direction. And so the displacement is in the same direction as the wave velocity. That's the definition of a longitudinal wave. And the most common would be a sound wave, but also some earthquake waves are also longitudinal waves. So if you think back to your earth science, those S waves and those P waves, those are transverse and longitudinal waves. All right, so one of the things that you were asked about was the difference between velocity and frequency. And this is kind of a hard question. So when you did your web quest, you saw this animation. And I want to make sure that we're really clear on the difference between velocity and frequency. So if you look at one little white dot, that moves up and down. And one complete up and down cycle is a complete wave. And how many of those complete waves occur each second is a frequency. So right now, that's on a low frequency. So go ahead and let's put it up to a high frequency. So you can see there's more waves per second. So that's a higher frequency. Now that's very different from a wave velocity. A wave velocity is actually how quickly the wave travels from one place to another. So the easiest way to do that is to trace a crest. Do you see my mouse cursor moving with that crest? That is the wave velocity. So what I'm going to do is I'm going to decrease my frequency again. So I'm going to go down and I'm going to trace my wave again, but this time at a lower frequency. Right? Fewer waves, but you're going to notice that my cursor is moving at the same speed as it was with the high frequency wave. It's a little easier to trace because it's more clearly defined, but that wave speed is the same. Ooh, there we go. And so the speed of a wave is not going to depend on the frequency, but it is going to change our wavelength. All right, so let's go back to make sure that we're very clear. So what's the difference between a frequency and a wavelength? The biggest difference is a frequency is how often a wave repeats itself. So how often those little white particles move up and down. And then the velocity is going to be how quickly that wave travels across the screen. And then the next question that we probably need to ask ourselves is, what's the relationship between frequency, velocity, and wavelength? So in your applet, you saw the relationship between frequency and wavelength. And we can actually look back at the applet that we were just looking at. And I think I can pause it. Absolutely. So if we were to mark a wave on this one whole wavelength, we could go from this point to this point, right? That would be one whole wave. And then if we had a higher frequency, we see that we have a much shorter wavelength. So if we went from this crest to this crest, or we went from this point here to this point here, we're going to notice that that's like half as much of a length. So there is an inverse relationship, meaning if our frequency goes up, our wavelength goes down. And the relationship that summarizes this relationship is velocity is equal to frequency times wavelength. So if you haven't already, I'd be taking a few notes on these things. And you're going to notice that the velocity is measured in the unit of meter per second. Our frequency is measured in the unit of hertz. That's cycles per second or waves per second. And then here's that fun little symbol again, that wavelength, lambda, that's in the unit of meters. Now, this value right here, this velocity only depends on one thing. And this is the tough thing about waves. It only depends on medium the wave is traveling through. So light always travels the same speed in a vacuum. It doesn't matter if it's red light or yellow light or green light or UV light or infrared, all of those travel at exactly the same speed. And all those things that I just listed there all have different frequencies and different wavelengths. So if we think back to the relationship between frequency and wavelength, we have an increase in frequency. Remember, we had a shorter wave, or a decrease in our wavelength. So that makes sense. If our velocity stays the same and we increase frequency, our wavelength is then going to have to go down. So you're going to be asked to do a couple of example problems with this relationship of velocity is equal to frequency times wavelength. And so we're going to do one example together. So I'm going to ask you to read this problem. We'll read it together. And then I'm going to ask you to pause the video. And I want you to start identifying the things that you know. And if you feel comfortable, jump in and do it, right? Okay, so we've got bats, and bats can detect small insects. I don't know if you know anything about bats, but they use something called echolocation. So they send out sound waves that we actually can't hear. They're too high for us to be able to hear. And they get those that information back, and they can detect bats that are little little bitty teeny. So they can detect bats that are approximately the size of 1 wavelength. So what is the minimum frequency of sound bats are required to detect an insect that is 0.57 centimeters long? So it also says assume the speed of sound is about 340 meters per second, which it is at about room temperature. So about like 20 degrees, 30 degrees Celsius, or about 60 to 70 degrees Fahrenheit. Okay, so what I'd like you to do is to pause the video, identify the things that you know, identify the things that you want to find, and then try to calculate that. All right, so pause. Okay, we're back. Maybe you just waited for that pause, or maybe you actually paused. We'll see. I don't know. I can't tell because I'm here at the other end of my computer. But all right, so the question asks us, what is the minimum frequency? All right, so I'm going to put a circle around that, and I'm going to label that with my lowercase f. Of sound waves required for the bat to detect an insect that is 0.5 centimeter or 0.57 centimeters long. And so that's actually going to be, we're actually going to need to put that in meters, aren't we? So we're going to need to put that in meters. This is 0.0057 meters. And that's going to actually be our wavelength. And then this right here is going to be our velocity, right? That'll be our velocity. So we'll use our relationship that velocity is equal to frequency times wavelength. And we'll multiply, or we'll substitute in our values. And I actually have a correction that I need to make. This guy needs to be in meters. So let's change that into meters. 0.0057 meters. So then we'll take our 340 divided by our 0.0057, and we will get a frequency, a crazy high frequency of 59,600 and about 50 hertz. And for us, it's hard to know because most of us probably don't have a lot of experience. Is that like a realistic value? And actually, it is. The range of human hearing is between 20 and 20,000 hertz. And so when bats use that echolocation, they're using something called ultrasonic, so like above the frequency that humans can hear. So they would use frequencies up to 60 or 70,000 hertz in order to be able to locate where their insects are that they want to eat. Interestingly enough, the motion detectors that we use in the classroom operate on very similar principles. They use sound waves to bounce off us and detect where we are. They're just probably not quite as sophisticated as what bats can do. All right, friends, well, I hope that this was helpful for you, and I hope that you are able to, I'm stopping sharing here. I'm trying to do too many things at one time, which is probably my problem. All right. Hopefully this was helpful for you, and give me some feedback. Let me know if that was good. It's great to talk with you today. Hope to see you all soon.